Good afternoon, everyone. Thank you for joining the NOAA Central Library today for our NOAA Innovators Series. We're very excited to have you here today. Just a quick housekeeping. If you have questions, please place them in the question panel. We will hold those until the end of the presentation. If you are having any audio or visual issues, I suggest you try logging out and logging back in. That usually clears it up. If you do have a persistent issue, I request that you try and chat me or email library.brownbag@noaa.gov, and I will try and help troubleshoot that. And without further ado, I'm going to turn it over to Tiffany House to introduce our speaker.
Thanks, Katie. Good afternoon. Thanks for joining us today, everyone on the line. My name is Tiffany House, and I am the NOAA SBIR Commercialization Specialist. And I'm going to talk about the NOAA SBIR program and then introduce Tim. The NOAA SBIR program provides competition-based awards to small companies for R&D to transform their innovative ideas into commercial products. All SBIR proposals must directly benefit the NOAA mission and have excellent commercial potential. Oscilla Power received an SBIR Phase 2 award in 2010. Since then, they have continued to develop their technology. This presentation explores the concept of using microscale wave energy converters as power sources for instrumentation and other low-power ocean applications. Dr. Tim Mundon has 20 years experience working on the development of wave energy and is currently the Vice President of Engineering at Oscilla Power. Dr. Mundon received his Ph.D. in 2005, where he researched optimization of wave energy devices. He has experience working on the design and development of a number of different wave energy devices. Today, he will give a picture of where they are right now in their technology development. It is my pleasure to introduce Dr. Tim Mundon.
Thank you, Tiffany. It's a pleasure to be here and chat to everybody today. So as Tiffany said, I'm the Chief Engineer with Oscilla Power, and I'm going to give you a little bit of a background as to Oscilla Power, how we got to where we are, and some of the work that we're doing at a small scale, or concepts that we have at a small scale that might be useful for ocean observations and ocean observing. So for those people who are not aware of Oscilla Power, we're a wave energy technology developer. We're developing the Triton wave energy converter, which you can see on the slide in front of you. A little bit of background about Oscilla Power. We were formed in 2009 by Raoul Chendré and Balki Nair, and the goal was to develop technology to extract energy from ocean waves. We originally started in Salt Lake back in 2009, and then we moved to Seattle in 2013, which was when I actually joined the company. We've now got an office in Edinburgh in the UK and also in India, but we're still pretty small. We only have 7 people, or 7 full-time people. We have a number of part-time people spread around. Actually, what's interesting here on the right, you can see an image of the architecture for the wave energy system that we have developed. There is a surface float, which is in yellow at the top, and then hanging beneath that on 3 tendons is ring-shaped reaction structure. This is what's known as a 2-body wave energy device. The relative motion of those 2 bodies is what generates power. So the motivation behind what we were doing is really about the size of the resource. I doubt that I'm telling anybody anything they didn't already know, that energy that can be provided from waves is very significant. If we just look at the US alone, it can provide, according to a number of different studies, the number varies, but I think a reasonable estimate is around about 1,000 terawatt hours, and potentially up to 10% of US electricity demand. Globally, if you look at the image on the upper right, you can see the red areas, which is where wave energy is mostly concentrated. And One thing that's very important to note to start with is one of the reasons why this was so interesting is that wave is a lot more consistent, reliable, and predictable than other variable renewables. And it also provides a much better match with the load. And some of that has to do with the higher energy density that you get with waves, which actually are an order of magnitude greater than that of wind, which is in turn a greater order of magnitude greater power density than solar. And so an interesting observation then is you need far less space to extract the same amount of power. So there's a lot of reasons why wave is more attractive than some of the other variable renewables. But excuse me, that being said, it's also turned out to be extremely difficult to extract cost effectively. The first patent in wave energy was actually back in 1799, and people have been working on it ever since then. But even said, there's still no commercial wave energy devices to date. So, you know, it's a challenge, but there are some benefits, and that's why we all are pressing on hard to try and develop this technology. Now, a little bit about Oscilla Power and how we got here in terms of technology. As mentioned, we were started back in 2009, and actually the NOAA Phase 2 SBIR award was actually one of the very first awards that we got for our technology, to develop our technology. And a lot of things have changed since that point, so I'm not really going to focus too much on that award or what was found during that award. I'm more going to talk a little bit about what we've done since and some of the interesting things that we could be doing going forward. As you can see, what I show on the slide here is a little bit of the technology development that we've gone through over the years. We started back in 2009 with a very simple system based around material science that was a reverse magnetostrictive generator, effectively a solid state generator, which we developed for a while. And as in the process of developing that and then developing the marine system around that, we developed a number of key technology elements which we were able to prove at different scales. In particular, there you see there's a couple of ocean deployments that we did in 2013, 2014, and they really allowed us to develop the core technology elements that we have now. Around 2015, we really started to focus on the device hydrodynamics, which is perhaps a different route that other developers have taken, but this is what's worked for us. And then from 2015 moving forward, we focused on developing the device and its hydrodynamics. We were very successful in the Department of Energy's Wave Energy Prize, which provided external validation and allowed us to prove our performance against a lot of other people who were also in the space. We were able to, again, scale the technology up over the years till we get to where we are right now, and which is that we're building our first full-scale prototype, which will be going, which I'll talk about in just a second. It's a 100 kilowatt unit. So this is the 100 kilowatt community scale system. Scale is a little arbitrary when it comes down to wave energy devices, but ultimately we're referring to the amount of power that the system would produce, average power that it would produce in a maximum case, a little like a rated power for a wind turbine. Now this system we're currently building, its size is around about 10 meters by 7 meters. In the image on the right there, you can see the architecture that's across all our device, all the different sizes of device, which is the surface float with the 3 lines that connect to a ring-shaped reaction structure. Big advantage to this architecture is that all motion that is imparted on the float by waves is translated into energy. That energy is extracted by drivetrains inside the float. There are 3 drivetrains, one attached to each of those tendons. So this system will be deployed later this year in Hawaii for testing for a year. Now, a couple more images that that I have here of just the construction. These are a little out of date. We've gone a little bit further than this right now, but it's being constructed in Seattle, and you get some sort of idea for scale just by looking at some of these. But what comes next after this is in many ways the primary objective for us, which is a larger utility scale system, which would be a megawatt type of megawatt size wave energy device. Now this is the Triton, where the prior unit was called the Triton C. They share exactly the same architecture. There are a few things that are different. Obviously the size. This is 3 times larger physically. It's designed to be installed in arrays of devices, just like a wind turbine would be installed in arrays of devices, or solar. And the goal here is really to be able to achieve cost-effective, large-scale wave energy. There are a few things that you need in order to get to that point, and one of those, is anybody who's got experience with the ocean would realize, is that you have extreme conditions that you have to survive. And the Triton system has an integrated survival and also load shedding mechanism, whereby it ballasts the float. The yellow structure there is ballasted so that it sinks down in extreme waves just below the surface, as you can see in the images at the bottom, and mitigates all of the loads on the system. And that would be an automated process in the case of extreme events. If you look on the little graph there, that kind of shows the effect of submerging. One of the key advantages to this is that as the waves start to get very large, we can start to ballast, and the effect is quite gradual. And so what it means is that you get a similar effect to a wind turbine, where as the wind speed starts to increase in a wind turbine, the blades start to change their pitch and limit the load that's applied to the system. Similar situation here. But this is, again, I focus on this. This is specific really here for a very large system that has the ability to include all of the equipment that would be needed for something like this. And also, last thing to add here is that we've done, as you saw through some of the earlier slides, we've done extensive numerical modeling and validation of this, both at tank and numerically. So what does that mean in terms of roadmap? Well, Scylla is effectively focused on larger scale systems to date, or has been focused on larger scale systems to date. There's the 100 kilowatt Triton C, which you see here in green in the center, and then on the right there is the blue, which is the utility scale system. We've been progressing these tracks in parallel. The hashed areas is work that's being completed, and the boxes are drawn around tasks that are currently in progress through federal awards that we have right now. But what I wanted to talk about today was the left of the slide, which is looking at smaller systems, very small relatively, and looking at, what's the viability and opportunity in that space. Now, the next slide you see, I apologize. I found this image here from somewhere else, and I can't remember. I'm afraid I can't remember where, so I can't attribute it. But I really liked it, and it really highlights the different areas within wave energy industry that are of interest, and the sort of size and sort of powers. And what this really highlights is the magnitude of the different markets. In particular, the green circle indicates like typical utility scale market. It's a huge market, but it's huge powers, and it also requires very low energy costs. And that's a real challenge. That's been a real challenge to date. If you start looking at some of these other areas, perhaps there are opportunities here that can be easier to access and more enabling for those markets. And in particular, what's of particular interest is the ocean observation, oceanography area, and I thought that was something that that would be relevant to talk to about on a in a NOAA presentation such as this. So these areas might include, ocean sensing, ocean observing, climate change, measurements, etc., etc. In fact, to be fair, I don't know, and I can't really imagine the sort of opportunities and sensors that would be used. However, this is the idea of providing small amounts of power to enable persistent marine observations is something that's of a particular interest at the moment. There are a couple of initiatives that are going on right now with the Department of Energy and NOAA to look at this particular space. The Powering the Blue Economy initiative at DOE has kind of spurred out the Waves to Water Prize, which is effectively focused on a small-scale desalination type wave energy approach. And then the Ocean Observing Prize, which is NOAA supported, is also trying to look at specifically this area, trying to provide power for remote and applications where solar isn't practical, you can't replace batteries, you need persistent marine operations. However, you might think, well, why haven't we been doing that before? And the bottom line is that it's actually been a significant challenge to create any useful amount of power to date. And part of that is that sensors previously perhaps had more of a power demand than they do now. A lot of technology development has taken place and the power requirements for sensors are reducing. And so maybe there's an intersection between these two that now enables science to be done where it couldn't perhaps be done previously. But I think to move forward here, most importantly, I think we need to kind of define what do we mean by microscale wave energy or small scale wave energy. There are a number of definitions of scale, and I think it's somewhat arbitrary when it gets down to a smaller size. But personally, in my mind, I'm talking about systems that could be deployed by 1 to 2 people, such as the image at the right there where a wave rider is being deployed. Something where you're talking around about 50 kilos maximum for a single piece, so 2 people could deploy it. It would need to be a fully self-contained system. It's physically about 1 meter. That's when I say a microscale wave energy system, that's what I'm thinking of in my mind. So power for persistent ocean applications, with a mouthful. What does that mean? That enables a lot of more science to be done across the ocean. Sure, it's a smaller market for us as developers, but this is an enabling technology, I think. And from everything that I have heard, and I would love to hear back from the people who are listening in, even power as low as 25 watts, if it can be provided 24/7, 365, has immediate applications for the ocean observing and ocean science field. So I'm going to take a slight detour now, which bear with me. But for those on the call that are not intimately familiar with the ocean and waves, there's just a couple of things that I wanted to kind of highlight. It'll help in a subsequent couple of slides. So just a little bit of background here. An individual wave, a regular wave here, and if you see in the upper left here, is described by a height and a period. However, when you look at the ocean, real waves comprise many different regular waves that give you the sort of time series that you see there in the lower left. Now, we describe that statistically, which describes the amount of proportion of each of those regular waves, and that's known as a wave spectrum, which you see in the upper right. So that allows us to describe a sea state by its peak statistical values, such as the peak wave period and the significant wave height. And when we refer to the energy or power or characteristics of a sea state, we're referring to those peak values. So if we look at the image in the lower right, we're looking at the amount of power that's available in particular sea states. So on the horizontal axis, you have the period, and on the vertical axis, you have the height. And so you can see that as you get a higher period and you get a longer, you get a higher wave height and a longer period, you get significantly more power. And now, the other thing that we can bear in mind, we look a little bit of wave energy. I apologize to everybody on the call for this slide, but it's a requirement to have an equation in here, so bear with me. But really very simple here is that I want to describe that a wave energy device is just fundamentally a simple mass spring system. And that means it oscillates with a particular period. That is known as a natural period, and it's determined by a number of things, but effectively that is driven by the mass and the spring. The spring being the hydrostatic spring, so the buoyant restoring force, if you will. And there are, like I say, there are other things that will drive that period, but for simplicity, you can see that just those two characteristics will drive the period. Now, importantly, the maximum power you will get from that system when it's excited is when the excitation period, i.e. the wave, matches the natural period of the device itself. Now, from that equation, you can see that if you make m really big, you will make that period longer. And so that means effectively that bigger systems will have longer natural periods, and that's important. And you can do the same with changing the hydrostatic spring as well. Now, if we look at energy capture, before I talk more about this, I'm sure some of you are familiar with the distribution there I show on the left, which is what's known as a joint probability distribution. Referring to the wave height and the wave period, it shows how often those waves occur at a given location. Now, importantly here, we can see that almost all of the waves occur in a certain range of periods. And those are fairly long wave periods. In this case, we're in Northern Oregon, and the period is actually TZ, which is a little shorter. And for those people that understand what I mean, that's the zero crossing period rather than the peak period. It's just a different way of representing the wave period. Bottom line is that the systems need to be big in order to respond to those periods. And so utility scale wave devices tend to be very large, typically with characteristic dimensions 30 to 50 meters. You look at some of the images on the slide, you can see how big some of these systems are. Our system would be 30 meters in size. If we go to the bottom left of the slide, you have the ocean energy buoy, which is an enormous oscillating water column that is currently in Hawaii, hasn't been deployed yet. In the middle is the Polamis. Again, it's about above 100 meters long. It's what's called an attenuator device. That company, unfortunately, has gone out of business now. That was one of the very first potential high efficiency wave energy devices. To the right of that is the Ruello Penguin. That's another large wave energy device out of Europe. So these larger systems, they capture a lot of energy because they're bigger. And so those two factors together mean that most of the focus to date has been on producing big devices that produce lots of energy. But what about we wanted to talk about smaller size? And so there are some specific challenges that are directly related to that mismatch in natural periods. The problem is that when you build something small, and when I say small, I'm talking about the sort of size that I was referring to before, say about a meter or so, you get very short natural periods, which are shorter than the waves that exist. And so the amount of energy that's captured is very small. So that means you need to kind of come up with different ways of being able to capture, or how do you design the device so that its natural period is longer than it would otherwise be. But that's not the only thing. You know, there are other significant challenges. There's a lot of relative motion between bodies as well when they're small, and that's difficult to manage. Plus, static dynamic friction becomes a very large proportion of the energy that you're capturing. But there are still advantages here. There are far more manufacturing options available. It's faster to test. It's probably harder in many ways to develop a small device that produces tangible amounts of power than it is to produce a large device, in my opinion. So I kind of started here. This may be of use. These are my whiteboard skills that you see in front. Effectively, what you have here is my personal opinion on what types of wave energy systems would be most appropriate for microscale wave energy. And on the left, you have what would be a bottom fixed point absorber system. There's an anchor on the seafloor, some sort of instrumentation package, and then a float that would be on the surface. Great, simple. Challenges here, you know, potentially you've got really big wave heights that would mean that you'd need to kind of have a lot of relative motion there. But and others, but it's simple. The second one there in the center is effectively the same sort of architecture that the Oscilla Power system uses. It's a two-body system. There's a float and there's a reaction plate that's hanging below it. And then on the right, there is a bottom fixed pressure differential. This is a wave energy type of device that works by the relative pressure that's created above it. So if my animation works, you can see that as the wave moves above it, it compresses and expands the device, and that motion can be used to extract energy. This is quite exciting because it can be below the surface and it may have defense applications. So I wanted to investigate this, and so we went ahead and we developed a microscale wave energy device because we wanted to explore the magnitude of power that we might get out of this. So I'll admit we actually repurposed a small scale version, a scale model that we developed to represent one of our largest systems, and inside it we implemented a different drivetrain that was able to have a lot of relative motion, and effectively the system should act just like a complete self-contained wave energy device. Now, as I mentioned previously, the natural periods of these systems of this size are, you know, quite short. In this case, this system had a natural period of 1.5 seconds. And we then tested this. We were fortunate to get support from a Marinette in Europe, and we tested this system in real ocean conditions, but in a tank. So we were tested up to 0.5 meter wave height. Obviously, we couldn't do any bigger than that in the tank, but we tested in up to 0.5 meter wave height with appropriate periods that would represent full-scale conditions. And so I wanted to talk a little bit about some of the interesting conclusions that that really came out of this work. And so again, just to highlight, this is not numerical modeling. This is actually real test data that we got from experimentation in the tank. What we did is that we represented these 4 climates, and we used this data to determine power output, or measured power output, for an entire year. And with the 2 fields or 2 columns that I circle there are important here. First of all, captured mean power, that's average power over the course of the year. But on the right is a practical measure. So it's delivered constant power to a load. So within the system, we implemented a battery, and we used that battery as a buffer. So the power that was being produced by the wave energy device went into the battery, and then from the battery it went into a load. And so we changed the storage size to match the particular climate. And as you can see, you didn't need a massive amount of storage, quite an achievable amount of storage, to actually get quite a reasonable amount of constant power from these climates. the second really rather important takeaway from this is that if you look at the amount of power that's being produced in these climates, it doesn't actually change that much. And this is this is actually very significant. If you look at how the incident energy changes, it goes from just over 1 kilowatt per meter to 13 kilowatts per meter. So we've almost got an order of magnitude there in terms of incident power. But the output power doesn't really vary by more than about 2. So that's kind of significant. That means that we can actually get more power than we would think out of smaller wave climates like the Great Lakes or even the Gulf of Mexico. Actually makes this kind of viable almost wherever you go. And a lot of that has to do with the way that the wave periods are distributed. As I discussed previously, then how the device responds to the natural period is really very important. And so if you have a particular climate that has a common period that's quite short, you're going to get quite good performance. And so you can see that climates that have a generally low energy content tend to have a concentration of wave periods at shorter lengths. And so we actually get more efficiency in those cases. So that was really quite an interesting conclusion from some of this work. And it also indicated the sort of magnitude of power that we would get, which is in the order of, 20 watts or so. Now, what we wanted to figure out past this was how much can we improve this? And so we looked at 2 different things. This is still an arbitrary size, and remember this was, of course, a physical model with a geometry that was designed for a large wave energy device. We figured we could do a lot more, and we wanted to know that if we could develop, if we could improve the geometry, what sort of power out improvements could we get? And so we looked at taking the natural period, moving it half a second, and seeing what would be the consequence of the amount of power that you would achieve. And you can do that through a couple of different ways, which I won't go into in detail, but you can do it through geometry, you can do it through advanced controls. And if you look at the sort of power gain that we can achieve here, you find out that you get around about 30 to 60% power gain through these levels of optimization. This is actually somewhat significant because I think it's somewhat an aggressive target to be able to move natural periods about half a second. But nonetheless, it's significant because it keeps. We know that we can only get to a level of power of around about 50 watts, even in these cases. So it kind of sets an upper limit on what we might want to get out of these sort of climates in terms of average power into a load 24/7. So I think this is kind of the key takeaway that I wanted you to kind of get from this work we've done. There's certainly more improvements to be made. And some of the future work that we plan on doing really looks to use genetic algorithms to optimize the geometry of the floats in order to be able to get that natural period moved to get more performance out of the system. We actually have, I'm working with some people to look at doing that. We'll start this summer. Shortly afterwards, we hope to be able to do some work on looking at a very small scale, very long travel drivetrain and testing that in the laboratory. And then that will then spur construction of actual true microscale wave energy devices, which we can test. Big advantage, of course, here is that we can do it very quickly. We can go through, once we've developed the concept, it's very quick to be able to iterate, and we can come up with a concept, we can build it, and we can put it out there very quickly. So in conclusion, what I wanted to kind of highlight here is that a microscale wave energy of the sort of microscale wave energy converter of the sort of size that I described can provide around about 20 watts continuous power, and that power is somewhat independent, not completely, but somewhat independent of climate. That's even available in low energy climates where we would never typically have considered wave energy previously. There are opportunities for further improvements. All I'm doing with this work has suggested that this is a range of power that we can expect. The size of the device especially allows for rapid design iteration. One of the challenges that we see when we're developing at a utility scale is that these devices are very big, very expensive, and very tough risk tolerances. And that means that you've got to be absolutely sure before you spend X million dollars on building a prototype. For something of this size, there is new techniques in rapid prototyping that you can just bring to bear, and you can put something in the water with very little risk. And as a result of all of this, I feel like we have a real potential to be an enabling technology and open up the door to new measurements, new ocean science, all across the globe. And I want to leave it there and pass it back to you, because at the end of the day, I think when I say enabling technology, I think being able to develop a way of providing power is just one step, and then the community and the industry and the science would take it from there. So thank you all very much for listening, and I'm very happy to take any questions on the presentation I gave today.
Thank you so much, Dr. Mundon. Okay, we do have questions, and I'm going to start with the first one here that came in a while back. When load shedding happens, especially in deep water, do you consider the effect of internal waves, which can have much larger amplitudes?
So, okay, that's an interesting question. The internal waves can have much. Okay, so first off, simple answer here is no. Mostly because the system will be very close to the surface. If anything, it will probably still be exposed. It won't be directly below the surface. So most of the work that we've done says that we don't need to fully submerge below the surface to get maximum effect. The other thing about internal waves is that the force on the system, whilst you have a large amplitude for the internal wave, the relative buoyancy change applied, the buoyant force change on the system is actually quite low. So we don't at this point, unless we're missing something, we don't consider that to be significant.
Thank you. Next question. Have you considered coastal and estuarine applications as well?
At a small scale, that may be viable. Generally, estuarine applications tend not to have a very high incident energy content in waves, so they may not be that viable. However, the small scale where you're looking at shorter wave periods, they may well be of interest. The one thing that's missing here actually is good solid wave resource data at the 1 second range. I forget what that region is called within the wave spectrum, but right now, if you look at the WaveRider network and the wave data we have, it generally goes from about 4 seconds upwards, and there's not a massive amount of data globally or in many areas around about the 1 to 3 second range. So having more data about that would certainly help identify, more accurately the sort of power we could make at a small scale.
Great, thank you. Our next question. What considerations have been made for biofouling and recreational boating?
Okay, so that's a question with a lot of answer. So I'll try and be as brief as I can. So I can tell you about the system that we're deploying in Hawaii. The system itself has a anti-fouling paint on it, which prevents growth on the hull. The the tendons that connect the two bodies together, we would expect growth on those, but that will not affect the performance. So that's not necessarily problematic, although during the deployment, we'll inspect and monitor to see how that goes. So bottom line is that I think the same sort of techniques that are currently used for vessels would be what we would use to manage biofouling. There was a second part to that question. Can you repeat that?
Yes, the second part was considerations for recreational boating.
Yeah, so that's another good point. If we're deploying single devices, there is obviously the risk that people will, interfere with the devices themselves. In fact, that's perhaps especially a case for the system that we have in Hawaii. There's not much you can do, to be honest, other than just make it as safe as possible and not have allow access into the internals. There is certainly there's no real risk of somebody hurting themselves on the outside of the system. There's no high voltage or anything like that. But that being said, it's still not a safe place to be. So warnings. When we're I don't have a great answer at this point. We would hope people to stay away. The moorings themselves are below the surface, so not necessarily too much of a risk. But maybe if you you can maybe ask a follow-up question, and I'd be happy to kind of address a specific concern there.
Okay, great, thank you. Next question. Is there a power saving threshold when wave spectra are below sensor power requirements, perhaps a storage system within the buoy, or must the sensor package store for low wave conditions?
Yeah, I'll be completely honest and say we haven't necessarily looked at it in that level of detail. The analysis that I did was to identify a level of storage that would eliminate such a threshold. When I was looking at the analysis that you saw at the end of the presentation there, that does assume that power is available at all times. So yeah, I think that answers the question.
Great, thank you. Next question. Will you integrate CFD workflow with genetic algorithm optimization?
Wow, that's just asking for a computational implosion. No, absolutely not. It's the process of doing a genetic algorithm optimization for geometry is so complicated in itself that adding a CFD analysis in the output is impractical. Even looking at CFD analysis for wave energy converters is computationally too expensive anyway. What we are doing, and I won't go into it in a lot of detail here because it's a bit of an open forum and I don't want to waste people's time, but we are looking at what's known as a mid-fidelity model, and we've developed a way to be able to do an analysis of the geometry, the performance, in a relatively short space of time. So it's an approximation, but it allows us to evaluate each geometry and the power that each geometry provides using a mid-fidelity model that gives us a good approximation of what we would expect. And then we take that output and then we evolve it through the next generation of the genetic algorithm. But incorporating CFD would not be practical.
Thank you. Our next question has a few subparts. But first up, how do these systems survive or perform under extreme conditions such as storms, winter ice, etc.? Do you have any field results from that?
Well, obviously, we do not have field results because we haven't actually deployed one at a large scale yet. That'll be happening this year, and it's going to be in Hawaii. So we'll certainly get storms, but unlikely that we'll get ice. So how they respond, how they are expected to respond, is through the load mitigation that I described during my presentation, whereby the system is ballasted to mitigate the load on the system, and that allows us to survive in, at this point, up to 1 in 100-year waves on the US West Coast.
Okay, and you did mention that there may not be ice, but what do you expect would be the impact of ice on this operation?
I don't want to speculate, to be fair. Ice is, of course, potentially a challenge for larger, well, for all systems at high latitudes. So we haven't really looked at it, if I'm completely honest, at this point. Smaller systems may be better, they may be worse. That's something that's worth looking into.
Great, thank you. Next question. What is the business plan for the microsystem? Rentals or sales or a combination?
I'm open to discussions. We don't have a business plan per se for the microscale. We try to develop it to see the viability of a system of that size, and that's pretty much where it stops right now. We do have some, we have a proposal in the works, which I can't really talk about, that will allow us to be able to take that to another level. But at this point, there's no real bigger picture business plan on the smaller scale. I would love to take that to that level, but I don't, and I think we could do that quite quickly, but that's not discussed yet.
Great, thank you. We have 3 questions, which I hope we can sail through before the 2 o'clock hour. Next one is, how do you tether or secure a small scale device so that it is not damaged or swept away during extreme weather events?
Yeah, good question. I would actually respond to that one with, you know, exactly the same. With another question is, how would you moor anything at sea? You know, a wave rider has a similar type of mooring or requirement for mooring. This wouldn't be any different. A single point mooring potentially, and you could, there are, like I say, there may even be the possibility to have a system that is not moored. There is work that's being done by, let me try and remember, at Embari, Andrew Hamilton at Embari has been doing some work, done some work, I believe, if I'm not speaking out of turn, on actually having the device station keep itself through the motions, the interaction between the 2 bodies, it station keeps. That's not something we're looking into. We would just assume that there would be a mooring similar to a wave rider or other small buoy.
Okay, thank you. Next question. 25 watts continuous power is still a tremendous amount for the ocean observation community. Can a 2-watt solution be implemented into existing slack and taunt buoy mooring platforms without large CapEx?
That is something we looked at a long time back, and I would say not easily, if I'm honest, not without introducing risk. Certainly you can look at something like that. And I mean, if somebody's particularly interested to discuss that, I'd very happily follow up with them. Afterwards. My gut feeling is that, you know, it should be possible to do something where there's a 2-watt sort of range of power, but yeah, I don't want to try and solve the problem right now. I'm happy to talk more about that. My gut feeling is that it should be possible, but you'd have to come up with something completely different.
Great, thank you. You're speaking of power in terms of watts. What voltage then is generated by the system and subsequently stored in the battery storage device?
That's somewhat it's somewhat irrelevant. You know, that would be a function of the power conditioning system that you would have within the device. You know, it's almost impossible to answer, as we don't have a kind of a product that to be able to tell you what that voltage is. I will say though that you know, we could produce whatever was useful for that particular sensor package. It would be very straightforward, and you know, DC to DC converters and power electronics that you would install these days are very efficient, and so we could probably, I would imagine, we'd have no problem adapting to any kind of voltage requirements.
Thank you. Next question. Have you considered having any mechanism to change buoyancy and so change the K of the system in order to improve gathering energy for different wave periods?
There's somebody who's kind of been watching what's going on. Yes and no. As in, yes, as an industry, and there's actually some work that's being done by the DOE national labs to look at dynamic geometry and how that can be used. So we have not actually looked at that ourselves, although that may well come out of some of the work that we're doing right now on the geometric optimization. But I can say now that is an area that people have looked at and are continuing to look at. It's very interesting.
Right. And in a comment from the Great Lakes, the commenter is saying that there is an increase of winds during the September to November period, and this is when they see reduced solar output. So an integrated solar wave power system would be of interest.
Absolutely, and yeah, and that's something that we're also aware of. You know, I've looked at this specifically from a wave perspective, but you know, creating a coupled or combined system where you have wave and wind would probably be very, very attractive.
Okay, that appears to be the end of the questions from our online attendees, but I believe Tiffany House has a question.
Hey, Tim, thank you for doing the presentation today. I did have one question from one of your earlier slides. What are you doing, or what do you need to overcome the challenges that you mentioned, since there currently isn't a commercial market for this?
Wow. So we have a development pathway that I highlighted initially. And so what we need to do is we need to work through mitigating the risk on the different technology aspects, and then securing financing to be able to deploy at, you know, larger scale. So it really depends on the particular product that we're referring to. If we're talking about the utility scale system, I think that's fairly well laid out. You know, our next step is going to be to deploy a system in Hawaii, and then the step beyond that would be to develop a utility scale deployment, which should be a couple of years down the line. And then, you know, so we do continued development, investment, and validation of that technology. The second part, which I would say at a smaller scale, is the same thing with a faster return. So, you know, we would be looking to, as I can maybe go refer to the future work slide, which is, you know, we need to work through some of the challenges of the drivetrain and the whole concept, and that will then enable a product as a whole to come out of that work, and then we would validate that and test it, and that would all happen a lot faster, obviously, because of the size, than it would if we were trying to do that with a megawatt scale system. Does that answer the question, Tiffany? I wasn't sure. It was a little unsure.
Yes, thank you.
Okay.
Awesome. We did have one question come in while you were answering Tiffany, Tim. And possibly this was mentioned earlier, but if you could reiterate, how are you storing the energy?
So in this case of the small scale system, I'm assuming a small battery or a battery of a given size. And that size of battery would be different for the application. So far, we're assuming a lithium ion type battery, lithium Fe ion. I can't remember the chemistries, but there's some lithium ion chemistries that are quite reliable for marine use these days. So that's the plan for the small scale devices. Actually, it's a really interesting little segue that I can go down right now, because one of the things that we've been looking at is actually the power storage on a larger scale as well. And we've been looking at this through actually another SBIR award, which has been to look at the addition of storage on large scale arrays. And there are a number of underwater energy storage systems that we have been looking at integrating with an array of wave energy devices that can really increase the value of the power that's being produced. But that's at a large scale, so I don't want to digress too much. But for a small scale, basically batteries.
Wonderful. Thank you so much, Dr. Tim Mundon. I believe that is the end of our presentation. It is the end of our questions. So if you do have a question and we didn't get to it, please put that in the question panel and we will pass it on after the presentation and you will be answered offline. And with that, thank you everyone and have a wonderful afternoon.
Thank you.